students, in physics in the section optics, let's see another experiment now, right? This is an experiment where we are going to find the critical angle of a prism. Finding the critical angle of a prism. Let's try to understand what is meant by critical angle. We already studied that in theory. Still, we'll recall the meaning of critical angle. When light travels from a denser medium to a rarer medium, at one particular incident angle, it will get totally internally reflected without refraction and will travel through the common surface. At this instance, the incident angle in the denser medium is known as critical angle for the two media. See what that means. Let's take a surface like this. Let's say this is glass and this is air. In glass, right, consider a ray in this direction. It reaches the surface here. So what do we do? When the ray enters into another medium, at the surface, at the common surface, we draw a normal. Let's draw the normal. That will be the normal. You know, glass is more dense medium. Glass is the denser medium and comparatively air is the rarer medium. Then what will happen when it goes from a denser medium to a rarer medium? It will refract away from the normal. It will refract away from the normal. So, how the refracted ray in the other medium, it will be, the refracted ray in the other medium will be like this. We studied this. Right? Let's say this is I and this is R. Now, what will happen when you increase this I, right? Imagine if I is 0, what happens? Without any deviation, it goes straight. I is 0, R is also 0. Then little by little you increase I, R will increase. At some point, see, I'll show you another ray in black color. Right, consider an incident ray like this. This ray, at some point, for some incident angle, this ray would travel like this. That means it doesn't emerge into the other medium, right? It emerges, it travels in the surface itself. It travels in the surface itself. If I increase the angle beyond this, let's say an angle greater than this, let me draw another ray. A ray that has an angle, incident angle greater than this angle, the angle of this black color ray I have drawn. Then what will happen? It will get reflected within the same medium itself. It will get reflected in the same medium itself. We call it total internal reflection. I need to tell you one thing. When the refraction happens, let's think about this I1. For this I1, most of the rays are getting refracted and they are emerging into the other medium. There will be a small proportion of rays that will get reflected here. Since majority of the rays are going into the other medium, we consider the refracted ray only. But after we have crossed a particular angle, when the incident angle is greater than a particular point, then what happens? 100% all the rays would get reflected. That's why we say it total internal reflection. Total. Right? There is nothing that emerges into the next medium. So there has to be a cutoff point, right? Up to an angle, it emerges to the next medium. Beyond that angle, it doesn't emerge into the next medium. That cutoff point is what we call critical angle. At that cutoff point, this black color ray you can see, that's how the ray would travel. Right? It doesn't emerge into the next medium. It doesn't get reflected as well. It travels in the common surface. So this black one, if I mark this as I2, I2, this I2 is what we call critical angle. I2 is what we call critical angle. Is I3. Let me mark it as I3 here. I3. So I'm considering, I'm showing you three different angles, three categories of angles. Look at the first. When I1 is less than critical angle, what do you observe? Refraction happens. Refraction. That's the first one, the purple color line. Right? When I2 is equal to critical angle, what do you see there? It's not refraction, it's not reflection. I mean, even if it is refraction, it doesn't emerge into the next medium. It travels on the surface, right? It travels on the common surface. Ray is on the common surface. On the common surface. I3 is greater than C, total internal reflection happens. So sometimes they ask this in the exam. They give a ray and they say critical angle is this much and the incident angle is this much. Complete the path of the ray. So you need to check there the incident angle, is it greater than the given critical angle or is it less than the critical angle? If it is greater than the critical angle, it emerges into the next medium. If it is less than the critical angle, if it is greater than the critical angle, it gets reflected. If it is less than the critical angle, it emerges into the next medium. Right? So that's the concept of critical angle. Now we are going to see how to find the critical angle of this medium. How to find the critical angle of this medium. And one more thing you didn't know about critical angle, see, the refractive index of the denser medium N will be 1 over sin C. What is that? What is that? See, in this case, consider the black one, right? You know Snell's law. You know Snell's law. 1 and 2 sin I over sin R. This is when I, R, this is the first medium, this is the second medium. So with respect to first medium, second medium's refractive index is what they give like this. So here we have glass here, air here. What I want to find, let's say with respect to glass, air, because the ray is going in that order, it goes from glass to air, right? So with respect to the first medium, second mediums. So this is actually air's refractive index with respect to glass. How would that be? Sin I2 over sin 90. Why? Why? When the incident angle is I2, look at the refractive and refraction angle. It's 90 degree, right? With the normal, it makes 90 degree. So sin I2 over sin 90. Sin I2 means I2 is critical angle. Sin C. Sin C over sin 90. Sin 90 is 1. This is glass NA. But what I want to find is glass's refractive index. Then I can say ANG. With respect to air, glass's refractive index will be 1 divided by GNA. We studied this. GNA is sin C. 1 divided means 1 over sin C. Right? The refractive index of glass, the refractive index of the denser medium will be 1 over sin C. If we can find the critical angle, then we can find the refractive index of the denser medium also. How are we going to do this in an experiment? See what materials and apparatus are required for this. An equilateral prism with all three faces being smooth. A drawing board, drawing pins, white paper, optical pins and protractor. When we do the experiment, I'll show you like how to use each of these materials. Method. Keep the prism ABC on the paper and mark its position. Fix an optical pin O vertically and touching one face of the prism. Right. See, if this is the prism, right, if this is the prism, you fix a pin here, make sure it's touching the prism. Why does it have to touch the prism? Otherwise, like if it is away from the prism, then when it reaches the prism surface, there will be reflection, refraction, all that are going to happen. So you have to make sure there is no gap in between the prism and the pin. Sometimes the pin you find will have a pin head. If the pin head remains above the prism, no problem. Then you can leave the pin head above the prism. Still you can fix it closer. But sometimes the prism will be taller and the pin you have might be a short one. In that case, if you still fix it with the pin head will make a space between the pin and the prism. In that case, we will have to cut that pin head, remove it, and then fix the pin. We will have to do that. Sometimes once they have asked this in the exam, like why do we have to cut this pin head? Oh, what would you do if the pin is shorter than the prism? Then you have to say you have to cut the pin head, remove it, and then fix the pin such that there is no space between the pin and the prism. Fix it there. Then keep the eye close to A and observe the image of O through the face AC. Move the eye towards C until the image disappears. Basically, you have to start looking from here and then move towards here. Let me explain to you what really happens here. Listen to me. Let me take a prism, say equilateral prism. So this is the object you have kept. This is where you have fixed the pin. Let's consider that pin as the object. Now we are telling you, you must keep your eye closer to this point and observe. So how can you get the image of this pin here? Let's look at the possibility. See, a ray should have gone to this side, gets total internal reflection there, it gets reflected, reaches this surface. Here it gets refracted, it should come out. That's what the possibility, right? So let's see how to draw that. Let's say a ray that reaches here will get reflected, right? And then here in this surface it has to get reflected away from the normal. So you keep your eye from here, you can see the ray from the pin reaching you. Then you will see an image of that. For this condition number 1, the reflection should have happened here. For the reflection to happen, if I draw the normal here, this angle, let me call it I1 should have been greater than C, right? The incident angle on a glass air surface, if it is greater than the critical angle, then only the total internal reflection would happen. Then only you will see this, see the image. Now let's move further. You bring the eye towards here. What will happen? A ray that leaves from the pin reaches here, gets reflected, and then here again if you draw the normal, it has to get refracted away from the normal. You must be able to keep your eye here and observe the image of the pin, because the ray started from the pin and it reaches you, so you must be able to see the image of the pin. But at this point when we draw the normal, and if I mark this angle as I2, do you understand I2 is less than I1? If I mark this angle as I2, do you understand when this point goes further and further up, the incident angle becomes smaller. I2 is smaller than I1. I2 is smaller than I1. What will happen when this point goes further and further up? at some point the incident angle here would become equal to critical angle. At some point it will become equal. Let's say another line. A ray that reaches the surface like this. Assume the angle here is C because it reduces. It reduces. At some point it has to become equal to C. Let's say C is 40 degree. Okay. Maybe here it is 50. 50 degree it gets total reflection. Here it might be 45. Again total reflection. Assuming C is 40. Just assume. And at some point it will become 40. When it is 40, what will happen? At this point, it will travel along the surface. It will not get reflected inwards. It will travel along the surface. Then this is where the ray is going to come. Which means this is C. Which means when you are moving your eye from here to here, after a point, you will not see the image of the pin. You will not see the image. Just when you are coming closer to critical angle. When you are at critical angle, the ray would travel in this direction. Imagine if the angle reduces further. If this is the angle, that incident angle has to be less than the critical angle. Then what will happen? The ray would get reflected and it will go out. Understand? I started from here. The first one I observed, it was here. The angle was much bigger. It would be above the critical angle. Reflected, refracted, we get it here. Another point, reflected, refracted, it comes here. Then when we further move, that means when I move my eye towards this side, the ray has to come from here. But here the angle became equal to critical angle. It was reducing little by little. At some point it became equal to critical angle. The moment it became equal to critical angle, you will not see the image on this direction. The image, the ray would travel on the surface. If the incident angle further reduces, it will get refracted and it will emerge into the other media, which is air. Clear? Right. So what we are going to do in this experiment, we will keep our eye here, keep moving towards here. We will find the last point where we can see this image. Last point where we can see the image, that will be very close to the critical angle. From that, even if you move 1 minute of an angle, then it's critical angle, you won't see the image. This is what the critical angle, how we find it. Start from here, you can see the image of the pin. Keep moving your eye until you see the image at last. The last point you see the image is almost the critical angle for you. Clear? Right. At the last instance when the image of O was seen, fix two pins P1 and P2. When you see the last image, that means look, when you keep your eye here, you saw image, it was good. When you keep your eye here, still you can see an image. Okay. When you keep the eye here, you don't see an image. Even if you move a little bit to the other side, you don't see an image. So that's the last instance where you are seeing the image when you are moving in this direction. At the last moment when you are looking from this side, you will be able to see the pin somewhere, the image. With that to be aligned, fix another two pins. So that the two pins you are fixing and the other pin, all three must look like collinear. They must look collinear. They must be in the same line, fixed like that. After fixing those two pins, now what you can do, you can remove the prism because you already marked these sides, right? You can remove the prism and draw the lines. I'll show you what lines you are going to draw. Listen. Now once you remove the prism, what you are going to see in your paper, what you will see in the paper, the prism's borders would have been marked. You will have a point here where you fix the pin. You can see the hole where you fix the pin. And then here you have the two pins. This is all you will see in the paper. See what we are going to do. First, connect these two lines and extend it until it reaches this surface. What name we gave for that surface? A, B, C. So let's say this is A, B, C. Connect these two. This is where you marked, you fixed P1 and P2. Connect these two. So that gives you the emergent ray at the critical angle, just before the critical angle, which is almost the critical angle. Just before the critical angle, the emergent ray is here. Right? Then what you do, from this point, this is what O, from O you draw normal to AB and extend it to the other side. Let me draw that in dotted lines. Right. Let me mark this point as M. And then extend this OM such that the distance of OM is equal to another point here. Let's say I. Here OM and MI should be equal. You have to construct the line OM such that OM is perpendicular to AB. And then you extend the line until it becomes equal on the other side. OM equals MI. Extend it. Which means, imagine whatever the rays that starts from O gets reflected here, reflected here, reflected here. All of them should look like they come from I. You know why? When the reflection happens on this surface, this is like a mirror. On a mirror, when reflection happens, it's like a mirror. On a mirror, the object distance and the image distance are equal. That's what I have done here. Object distance, image distance. O for object, I for image, M for mirror. This is like a mirror. So you draw the perpendicular, take equal distance, you can mark the image. You can mark the image. Right? This is how you identify the image's location. Now what do we do after that? See, we have constructed this line. Okay? Now what we do, see, from this line, from this point, connect this point. Let me give name for them. Let me mark it as Q. Q already you know because you have drawn P1, P2, extend it, find where it intersects with AC, that point is Q. Extend this line. When you are drawing this line, this part we can keep it as dotted lines. Right, that will be the dotted lines. Why did I draw that? I'll show you. So let's connect these 2 points. Right. Now, the path of the ray would be like this. See how that worked? Any ray that reflects here and comes to the other side have to initiate from here. It should look like it's coming from this image, right? Because imagine anybody sees here before this border, if we can observe, it's within the glass though, but the image for anybody who can see these lines, the image is this. Let me show you another line. Look at this. Another line would be like this. Understand? So anybody looking from here, see, there has to be the first reflection. After the first reflection, the line should, the ray should look like it comes from I, right? From there, and then it gets reflected, it comes to the other side, right? So how do we do? First we located the image. It's very easy to locate the image because the object distance and the image distance has to be same. It's like a mirror. So draw the normal, find this image. Then connect that point to this point where the emergent point is. Connect the emergent point. Then this part is going to be the reflected rays path. Reflected rays path. And then you can connect these two to find the incident rays path. The incident ray, reflected ray and the emergent ray. The blue color line shows the critical angle because that was the last position you saw, that you fixed these 2 pins when you last saw the image when you're moving your eye on this direction. Now where is the critical angle? On this surface, the incident angle has to be critical angle. The normal is this. If this is the normal, this is critical angle and this is also critical angle. Why that is also critical angle? The incident angle and the reflection angle must be the same. Incident angle and the reflection angle must be the same. Therefore, C and C. if we can measure this angle, O, let me mark this point as P. What name have we given? P, yes, OPQ. OPQ. This angle will be twice of critical angle. It's very simple. It's all about finding where you last see the images, fix two pins, connect them here, locate the image. From the image you draw one line here and draw the incident ray. Incident ray, reflected ray and the emergent ray at the critical angle. Where is the critical angle? On this surface, the incident angle is equal to critical angle. Right? Now remove the prism and pins. Draw line QR connecting P1 and P2 where Q is point on AC. Yes, we connected this there. Draw the perpendicular OM from O to AB and extend it to I such that OM is equal to MI. Yes, we did that. I is the image of O due to the reflection of rays on face AB. Draw IQ and mark the point P where IQ intersect AB. Draw IQ, connect I and Q, mark the point where it intersects this surface P. Now OP and PQ are the incident and reflected rays on face AB at critical angle, at an incident angle equal to critical angle. This is C. Draw PN, the normal to face AB at point P. Angle OPN will give the critical angle. Angle OPN will give the critical angle. Measure angle OPQ and it will be the twice of critical angle. OPQ will be twice of critical angle. Right? So you keep your protractor, measure this angle and divide by 2. That has to give you the critical angle. Clear? This is what the experiment we are going to do. Right? Once we get the critical angle, then n equals 1 over sine c. N is the refractive index of glass, that equals 1 over sine c. That will be easy. Shall we do the experiment now? Get the critical angle and see what n we are getting. Dear students, we are going to see another experiment in light. One of the sections in physics, light, we are going to see another experiment. What we are going to see in this experiment is finding the refractive index of glass. But to find refractive index of glass, we already studied different methods. In this experiment, what we are going to do, we are going to find the critical angle of a prism. Using a prism, we are going to find the critical angle of glass. And using critical angle, we can find refractive index. First point, what do you mean by critical angle? When a light ray travels from glass to air, what can happen if the incident angle is below a certain value? It will get refracted and it will exit or it will emerge into the air. But if the incidence angle is bigger than a certain value, it will not emerge into the air. It will get reflected. There will be total internal reflection happening in that boundary, in that border. And again, it will get reflected into the glass itself. So that value beyond which the reflection happens, below which the refraction happens, that threshold is what we call critical angle. So if the incident angle is less than critical angle, there will be refraction. If the incident angle is greater than the critical angle, there will be reflection. That's how the critical angle has been defined. So now in this experiment, we are going to use a prism and find the critical angle. And how critical angle and refractive index are connected? Refractive index is equal to 1 over sine of critical angle. 1 divided by sine critical angle will give us the refractive index. So when we use glass and air, with respect to air, glass's refractive index can be found like that. So for that purpose, let's see how to find the critical angle. So first we will see what materials and apparatus are required to do this practical. So if you look at the materials and apparatus required for this practical, we need a glass prism. Using this prism only, we are going to find the critical angle. and we will be finding the refractive index of this prism. We need a drawing board. We need a paper. To fix the paper on the drawing board, we need some drawing pins. We need some pins to mark the rays, incident ray and the emergent ray has to be marked using the pins. We need a pencil to draw the path of the rays, and we need a protractor to measure the angle, and usually in practicals we use meter ruler to draw the lines. This is all the materials and apparatus required to do this practical. So first what we do, we will take this paper and fix it on the drawing board. Let's fix the paper with the drawing board. Right. What we do after that, take the prism, keep it somewhere in the middle of the paper and draw the borders of this prism. Draw the borders. Usually we have to use pencil for this, but here I am going to use a pen because it will be more clear for you. But when you are doing practicals, make sure you use pencil. You should not use a pen. Draw the boundaries of the prism. Then what we do, take a pin and fix it close to the prism. There shouldn't be any space in between the prism and the pin. So when you are fixing, there is a couple of things that you have to understand. First thing, don't leave space between the pin and the prism, because if you leave space there, then the rays coming from the pin will get reflected at the face of the prism. So to avoid reflection at the face of prism, what we do, we fix it very close to the prism without leaving any space between the prism and the pin. Second thing, to fix it so close to be attached to the prism, make sure the pin head is above the prism. Suppose if this pin head remains below the prism, then it will not allow you to fix it attached with the prism. There will always be a space between the pin and the prism. So if you have a smaller pin which is not taller than the prism, you will have to cut and remove this head and then fix it. But I don't have a problem because I have a long pin. So let's fix it. Right, so you have fixed the pin now. Now let's analyze what will happen to the ray that comes from pin into the glass. So you can see the ray that comes from the pin into the glass will first reach this surface. I am talking about the rays that come from this pin to this surface. What will happen if the incident angle on this surface, incident angle on this face, if it is below the critical angle, then they will get refracted and that will emerge on this side. They will emerge on this side. But if the incident angle on this face is above the critical angle, then there won't be refraction. Instead, there will be an internal reflection. What's the meaning of internal reflection? The rays that reach this surface will get reflected again within the glass itself. So what will happen after internal reflection? They get reflected here and again they will reach this surface, glass air surface. From this surface, they get refracted and they will come on this side. So from this face of this prism, I will be able to see the internally reflected rays coming out, emerging from this face. So understand, when I look at this image from this face, on the right side, if I look from this end of this face, right side, this end of this face, I'll be able to see the image very clearly, because the rays that are coming from this end will have a high incident angle. See, they have to come to this point and then come out. So they'll have a high incident angle. Remember, incident angle has to be measured from the normal, not from the face. So the rays that reach here will have a high incident angle. So surely they will have internal reflection happening comfortably, and I'll be able to see the image from this side. But what will happen if I move my eye from this point towards my left? Imagine if a ray has to come from this point, then it should have reflected somewhere at this point. So when you consider a point here, the incident angle from this pin is low, which means the internal reflection might not happen around this place. So practically, when you move your eye from your right to left, when you are at the right, you can see the image clearly. When you move your eye from right to left slowly, at some point, the image will disappear. You will not be able to see the image in the left side of this face. Right? So I need to find out, I have to start from my right side and slowly move my eye and find out the point at which the image disappears. That threshold point tells us, or that the ray that comes at the threshold point is having an incident angle equal to critical angle. I repeat, you can see the image from this end. Move your eye from this end to the left end. At some point, the image will disappear. So you need to find out the moment where image disappears. In that instance, the ray will have the incident angle and the critical angle will be equal on this surface. So all what I have to do, I have to look at the image from this end and keep moving my eye and find out where the image disappears. Let's try that. Now I can see the image of the pin very clearly. Very clearly. I'm moving my eye. Still I can see that. Still I can see that. Keep moving. Keep moving. Still I can see. Yes. At this point, the image disappears. See, you can repeat it again. See, I can see the image very clearly. Move, move, move. At this point, the image disappears. So, the last image I see, I'm going to fix 2 pins on this side to be collinear with that image. See, this is the last image I see. And another pin. Right. So what I have done, I have fixed 2 pins on this side to be collinear with the last image that I could see when I was shifting my eye from right to left on this side. When you are fixing these 2 pins, make sure you fix them in as much distance as possible to minimize the error. Now I have fixed the pins. I can remove the prism. I can remove the pins and see how the ray would have traveled within this prism and outside the prism. So let's remove the prism and pins. So now what you have to do, from the first pin, this is the phase where the reflection, internal reflection has happened. So I have to draw a normal. And that normal has to be extended such that, the the distance of the object and the distance of the image have to be equal. Image distance and the object distance have to be equal, right? So let me draw a normal, extend it to equal distance and mark where the image would have been of this pin. This pin will have an image on this face. So draw a normal, extend it to be equal to, the distance has to be equal. That means object distance and the image distance have to be equal. And let's mark the image first. That's the first thing. So how do we draw the normal? How do we draw the normal? Keep your protractor. Make sure the 90-degree line is aligned with this face and keep shifting it up until the point where the pin was fixed aligns with this horizontal line, 0-degree line. So this is 0 degree and this face is at 90 degree. So if you mark this 180-degree point, that has to be the normal. Right, see, this is 0 degree, this is 180 degree, and you kept 90 degree for this face, which means on this side you have 90 degree, on the other side you have 90 degree. Let's connect these 2 points. Then what you do? Measure the distance on this side, the object distance, and make it equal to the image distance. 2 centimeters. So 2 centimeters on the other side, the image would have been here. Now I have marked the image. That means due to the reflection happening on this face, the image of the pin should have been appeared here. Right. And then, so the ray that comes from the reflection on this face, again is going to get refracted here. For that ray, it will appear like it's coming from this point. So see what we do here. The emergent ray, let me draw the emergent ray. This is my emergent ray. For this emergent ray, what would have been the object? This image would have been the object for this emergent ray. So you connect this point of emergence, and this image 1, first image's point. This is how the ray would have traveled. This ray would appear like it comes from this image, and then the ray reaches this border, this face, glass, air, surface, and it gets refracted, it comes out. Connect the original pin's point and this point, the reflection point. All right. So now this shows how the ray would have traveled. This is how it reaches the first surface, gets reflected here, and it travels this way, and again it comes out. This is what I saw from this side. And you notice that when I saw the image from this end, I started moving my eye towards the left side, and this is the point where the image started to disappear, which means the incidence angle for this ray on this surface is equal to critical angle, because beyond this point the reflection happens. That means if the ray reaches this point or this point, the reflection happens. But above this point, let's say if the ray reaches here, this point, then the angle is less than the critical angle and the reflection did not happen. How do I know reflection did not happen? Because I could not see that from this side. So this is the last point where the reflection happens, which means incident angle at this point would have been equal to the critical angle. And you know, the incident angle and the reflection angle both have to be equal. So if I measure the angle between these two lines, that should give me twice of critical angle. Why? The incident angle is equal to critical angle. At the same time, incident angle and reflection angle are equal. So it has to be twice of critical angle. Let's measure this angle. I extended that line for me to comfortably measure the angle. So now you can see the angle from here, if you measure, we have passed 70 and then 75 is here. It is 74 degrees we are getting. So twice of critical angle, what we are getting is 74 degrees, 74. 2C equals 74 degrees. So we can find C based on that. That means divide by 2, 74 by 2, 37 degrees will be C. Now we will see how to find the refractive index of glass using this critical angle. Right, students, the readings we have got: OPQ angle 74 degree. Let me write that here, 74 degree, which means critical angle is 37 degree. 37 degree that we have got. N equals 1 over sine C. 1 over sine C, 37 degree. If you take the values for this from the table, right, and solve this, we are getting 1.6 as the answer, 1.6. It has to be around 1.5, but there might be errors in the experiment. So the answer we are getting is 1.6, right? So don't be too worried about the answers we are getting in the experiment, because experiments can have errors in that. But be clear with the steps, as I always say. More than the calculations, the steps, what steps we are following, why we are doing each of those steps, that is what is more important here. And one more thing I can show you. Now, look at this note. This method can be used to find the refractive index of a liquid as well. On this same method, we can find the refractive index of a liquid also. First, a wet glass slide should be kept on AB surface. Then, in the same method, the critical angle can be found. It will be glass water critical angle. This is our prism, right? Now what we do, we will keep a glass slide here. This is a glass slide. So in between what happens, it's water. Here what you have is water. Because it's a wet slide, here what you have is water. And what is this? This is glass. Same method you are going to do. You will fix a pin here and then draw the line. You find the critical angle, or find the last image you see, like what we did for glass. You'll get something like this. Right. Let's say this is N1, this is N2. Earlier we did not have to bother about N2 because it was air on the other side. The refractive index of air is considered to be 1. So we don't have to consider that. But this time we have water there, a liquid, which will not have refractive index of 1. I have to make it, let's call it N2. Right. Now if you measure here this angle, let me call it as 2C1, let's say C1. Last time we called C, this time let me call it C1. This 2C1. Then the refractive index of glass with respect to water. Remember earlier when we did only with glass without the water, we said glass's refractive index with respect to air was 1 over sine C. 1 over sine C. Right? Since it is air, we don't have to write A and G, we can simply say N. But this time it's not air, it's water on the other side. Water on the other side. Sine C. Sine C1. C1 you can measure from here. So what is this? With respect to water, glass's refractive index. With respect to water, glass's refractive index. I can rewrite this A. Glass's refractive index divided by water's refractive index. That's what WNG would be. Equals, this is what we studied in theory, sine C1. If you take it there, ANW ANG into sine C1. ANG into sine C1. Check that. A and G is what we marked as N1. A and W is what you have to find. Let's say N2 equals N1 sine C1. Let me repeat that. N2 equals N1 sine C1. C1 in this experiment you are finding it. N1, already we have done the same experiment for glass. We found N1. You can use that answer for N1 here. C1 you can measure, apply. You will get the answer for N2. You get the answer for N2. This is how you find the refractive index of water. Right? You keep a slide there. You keep a slide there. Wet slide. So there will be water here. Then when the refractive index, when the critical angle equals the incident angle, you know how to locate that, right? You start observing the image from this end, keep moving your eye, see where you see the image at last. At that point, you fix 2 pins, draw this line, do all those previous, drawings, construction, then you can get this ray diagram. After getting the ray diagram, you can get this angle. That will be twice the critical angle. But what is this critical angle? Glass, water, critical angle. Glass, water, critical angle. When you're writing the formula, you have to say glass's refractive index with respect to water. Glass's refractive index with respect to water will be 1 over sine C1. And then you solve it, you get N2 equals N1 sine C1. Clear? And one more thing I can say, the critical angle you are getting here would be greater than the critical angle you have got for air. How is that? Right. So here you have N1 and on the other side N is equal to 1, right? Okay. Here you have N1 and the other side N2 is greater than 1 but less than N1 because water's refractive index is greater than air but less than the glass. So what will happen? Then here the difference between the refractive index, difference in refractive index, difference in N is high. Difference in N is high. Right? Basically, relative to air, the refractive index is higher. Right? Then what we can say, let's say N equals 1 over sine C, right? So, when N increases, what will happen? C will decrease. Why 1 over sine C? 1 over sine C has to decrease. Sine C decreases means C decreases. C decreases. That's why here the C will be lower, here the C will be higher. Let me mark it as C and here C1 critical angles. C will be lower than C1. C will be lower than C1 because with respect to the next medium, glass's refractive index is higher here. It's higher. For example, the theoretical values we know, glass is usually 1.5. Is 1. So compared to 1.5, it's 1.5 times. Whereas here, 1.5. But the other medium, the rarer medium, it's not air, it's water. So N2 is usually around 1.3. 4 by 3, right? 1.3. 1.33. So relative to that, 1.5, it's higher, but not as bigger as here. Understand? Because of that, the critical angle you are getting here will be a bigger angle. Remember this, when N increases, C drops. N in the sense, if this is first medium, if this is second medium, 1 and 2 equals 1 over sine C. 1 and 2. 1 and 2. So when 1 and 2 increases, sine C should drop. Clear? Right? So there are exam questions on this experiment. We'll take those exam questions one by one and see how far we can answer them. Right. So see the questions I have taken 2008 A-level question. We'll see what it is. Two monochromatic rays of light with angles of incidence theta 1 and theta 2 theta 1 is greater than theta c, theta 2 is less than theta c, where theta c is the critical angles of glass are falling on a glass air interface as shown in figure 1. So this must be glass air. Complete the paths of the rays. So you know, if the incident angle is greater than the critical angle, total internal reflection will happen. If the incident angle is less than the critical angle, it will get refracted and go into the next medium. Theta 1 is greater than theta c, which means here the total internal reflection must happen. According to the law of reflection, the angle of reflection also must be equal to the incident angle. Incident angle is theta 1, so reflection angle is also theta 1. Here the incident angle is less than the critical angle, it will get refracted into the next medium. Draw the normal. Yes. It gets refracted away from the normal, Let me say theta 3, right? It gets refracted away from the normal. From a denser medium, when it goes into a rarer medium, from the denser medium to rarer medium, it refracts away from the normal. Next, you are asked to determine the critical angle of glass by the method of total internal reflection. A prism is placed on a white sheet of paper in such a way that a vertical pin M is in contact with face AC of the prism as shown in the figure. The boundaries of the faces of the prism are drawn on the paper. In this experiment, the pin M has to be placed in contact with face AC. State the reason for this. Look at this. If this is the prism, right, let's say A, B, C, this is the pin. So why it has to be in contact with the pin? Because if there is a gap between the pin and this face, then there will be refraction. The light ray that starts from the pin, when it reaches the face AC, there is going to be a refraction. To avoid the refraction, to ensure it looks like the ray starts within the glass itself, we keep it in contact. So why do we keep it? Why do we place the pin in contact with the surface AC? To ensure there is no refraction at face AC. To ensure no refraction happens on surface AC. This is the diagram ACB. When you move your eye from B to C while looking through face BC towards AB, what change of the image of the pin M do you expect to observe? What will happen, you know, when you move in this direction, B to C, here you will have a clear image. After a point, the image will not be seen, right? Until a particular point, you can see the image. After that, you cannot see the image. Let's say until a particular point, the image of the pin will be visible. After that point, it will not be visible. That's all. Very simple, very simple. Next, how do you detect the path of the relevant emergent ray experimentally using two other pins? The location of two pins are marked as X and Y. What do? You observe through, what's the side? BC, is it? Yeah, you observe through BC and fix two pins to be collinear with the image of pin M. Fix two pins X and Y to be collinear with the image of M when the image is last seen. Right? When you are moving your eye from B to C, when you see the image last, at the last point you see image M, fix 2 points X and Y. Draw XY. Draw XY. It will be the emergent ray. Emergent ray. Very simple, very simple. Next, write down the remaining steps in the order that you would follow to construct the ray diagram. Use figure 2 or so to illustrate the steps in the construction of the ray diagram. First, we will see the construction, then we will come back and write it. Now, what do you do? So, you have already fixed points X and Y. First, what you do? Draw the emergent ray. Draw the emergent ray. Then, what do you do? From point M, draw the normal line to AB and extend this normal line until I such that, let me call this point as N, such that Mn and Ni are equal. Mn and Ni are equal. Then what do you do? Connect these 2 points and find where this line intersects AB. Let me mark that as P. Then what do you do? Connect MP. Now, if you measure MPY, this will be the twice of critical angle. That's what we did in the experiment, right? So, now we have to draw, we have to write the rest of the steps. The point Y should be somewhere here. Point Y, you can't fix a pin on the prism itself, right? So, point Y will be somewhere here. Let me call this point as Q. Let's call this point as Q. Now, let's say extend XY to meet, what's the name of that face? BC at Q. Draw MN, the normal to AB and extend till I such that Mn is equal to Ni. Do that. Then what you do? Draw IQ and P is the point where IQ intersects, what's the name of that face? AB. Intersects AB. Then what do you do? Draw MP. Right, now you know MP is the incident ray here, PQ is the refracted ray, and this one QX or YX will be the emergent ray. This is the experiment we did. What measurement would you take from the ray diagram? Also clearly indicate it on the ray diagram. What you have to measure on the ray diagram? You have to measure this one, right? Let's say this is theta. MPQ has to be measured. MPQ has to be measured. Next, you are asked to modify and repeat the experiment and determine the critical angle for glass water interface by forming a thin layer of water on surface AB as shown in figure 3. So as we discussed, you keep a glass slide having a water layer in between the prism and the glass slide. Where would be the new location of the image of pin Y relative to the image obtained in part B above? First, without the water layer, only the prism was there. There was an image. Let's go back to that point. Now see, this is the prism. This is where the point M is. You draw the normal. This is where the image is. Right? So when you find the image, what happens? This side acts like a mirror. It is like a mirror. Why? There is reflection happening. Reflection. Total internal reflection is happening. Whenever reflection is happening, that face acts like a mirror. In a mirror, on a mirror, the object distance and the image distance have to be equal. Right. What will happen when you place the glass slide and water layer? Here again the prism. You keep a glass slide. Now you have water layer in between. Right. Again the pin is here. Again you are talking about total internal reflection on this face. So if total internal reflection happens on that face, again it acts like a mirror. Again the same concept. On a mirror, object distance and image distance have to be equal. What would you do? Draw the normal. I. Right? So what's the difference you see between this one and that one? No difference. See, this surface, AB surface, acts like a mirror in both cases. And pin's position did not change. Therefore, the image's position also does not change. Relative to the image obtained in part B, no change. You can say no change. No change. Image's position doesn't change. You don't have to draw the diagram. Diagram I have drawn for you to understand. In the exam, you can simply say no change. Draw the new emergent ray in figure 3 relative to x and y. Label it as x dash, y dash. Figure 3. This is figure 3. This one. So, you know, this is where you had x and y. Let me mark x also. This is where you had x and y, right? Now, see, if you connected x, y, this is how the line would have been, right? If I go back to the previous diagram, I'll show you. This is where the critical angle is. But once you keep the layer of water there, the critical angle has to increase. Glass, water, surface, critical angle is bigger than, higher than glass, air, critical angle. Then what happens? The critical angle, the point P will get shifted here. It will further come down so that you get a bigger angle. Understand? The angle will be bigger. Yes? Then the emergent ray you would see somewhere here. So let me draw that. If this is xy, the emergent ray you get now would be something like this. Right? The angle also will be a little less and the position also will be different. It doesn't start from where xy starts. Q would have shifted towards B. The point Q we marked here would have shifted towards B. The angle also, the emergent angle will be less. Critical angles determined in part B and part C above are C1 and C2 respectively. Find an expression for the refractive index of water in terms of C1 and C2. See, for A and G, that means glass's refractive index with respect to air, I can say 1 over sine C1. A and G is equal to 1 over sine C1. Now we have done the experiment where we have a glass water surface, normal. This is how the ray travelled, 90 degree C2. If I name this as A and G and A and W, you can use the Snell's law. You can say A and G sine C2, A and W sine 90 degree. Sine 90 degree. Sine 90 is 1, right? So A and G ANG I can substitute what I have already got. What did I get for ANG? 1 over sine C1. Sine C1 into sine C2 is ANW. ANW equals sine C2 divided by sine C1. That would be the answer. Sine C2 divided by sine C1. So, the answer for ANW, the water's refractive index, you are getting sine C2 over sine C1. I already explained C2 will be a bigger angle than C1. C2 will be a bigger angle. So, sine C2 will be bigger than sine C1. So, the answer for this will be greater than 1. And we know the answer has to be around 1.33. 4 by 3 has to be the theoretical answer, right? We can expect something like that here. Clear? Shall we see another question now? Another one. 2001 A-level paper. The arrangement made by a student to find the refractive index of a prism is shown in the diagram. Two optical pins P and Q are used to trace the incident ray, PQ. The student has not fixed the pins properly. How will you fix them? What mistake do you think the student has done here? He has fixed them too close. There has to be significant distance between the two pins, right? So, we'll say we'll fix one pin closer to this surface and the other pin as far as possible from Q. Fix one pin closer to face AB and the other at considerable distance or significant distance, considerable distance from the previous pin. Both pins must be vertical. Make sure both pins are vertical, right? Next, how would you obtain the emergent ray in the experiment? How would you obtain the emergent ray? Look at this. You have to observe from AC. You will see the images of P and Q. Bring them collinear and fix another two pins to be collinear with those two images. Observe through face AC. Observe through face AC. Fix two pins to be collinear with the images of P and Q. Right? Draw a line connecting the new pins. That should give you the emergent rays. So, this is what we do in the experiment. Why can't we use a single pin instead of two pins in one above? Come on, you have to draw a straight line. To draw a straight line, you need at least 2 points. If you fix only 1 point, through 1 point you can draw any number of straight lines. Right? So, you can say at least 2 points will be required to draw a straight line. That's why we need 2 pins. Minimum 2 pins or 2 points. 2 points are required to draw a straight line. Okay. Next, label the following angles on the diagram. Incident angle I1, refractive R1, incident R2, emergent I2, angle of deviation D. So, first what we will do, we'll complete the path. This is the incident ray, this is the emergent ray. So, the refracted ray has to be in between. Also, let's draw the normal in both cases. That's how the normal will be for this incident point. Let's mark the incident angle with the normal I1. Make sure you mark it with the normal. Refractive angle R1. Then in the next surface, incident angle R2. R2. And this will be I2. I2. Angle of deviation, to mark angle of deviation, look at this, we'll mark R2 down here. This is R2. This is I2. I have to extend both these lines, incident line and the emergent line. That's the incident line. Extend the emergent line backwards. And this angle is what you mark as deviation. Deviation. Right. From the incident line's path, how far, by how much the emergent ray has deviated. Write a formula for D in terms of I1, R1, R2, I2. It's simple. It's simple. The deviation it has got in the first point and second point. First point deviation will be I1 minus R1. Second point deviation will be I2 minus R2. I2 minus R2. Let's write that. We studied that, we have done that several times in the theory. I1 minus R1, I2 minus R2. That will be I1 plus I2 minus R1 plus R2. R1 plus R2. For a particular incident ray, I1 is equal to 10 degree, R1 is equal to 6 degree. What is the refractive index of glass? You know, N equals sine I1 over sine R1. Sine 10 degree divided by sine 6 degree. So you take the sine table, find sine 10 degree, sine 6 degree, divide the answers, you will get approximately 1.6. When you round it, you get 1.6. Some students, without calculating, they thought it's glass. We usually get glass 1.5. They would have written 1.5 here, would have lost the marks. So don't take pre-assumed values for refractive index. If they say water, if they say glass, don't assume the numbers that you know. Right? When they give numbers, when you calculate based on the numbers they give, you might get different answers. They might intentionally give you to get different answers. Careful. What is the value of R2 if the prism angle is 6 degree? You know, A equals R1 plus R2. 60 degree equals R1 is 6 degree, R2. So R2 will be 54 degree, 54 degree. Clear? Next. Do you expect an emergent ray on surface AC for the above incident ray? Explain. What would be the problem there? If the incident angle is bigger than the, critical angle, then there won't be an emergent ray. There will be a total internal reflection happening. So let me find the critical angle. N equals 1 over sine C. So sine C equals 1 over N. N is 1.6. Correct? So when you divide 1 divided by 1.6, you will get 0.625. You can use a sine table and find what value is C. You will get C approximately 39 degrees. 39 degrees. Okay? Which means the critical angle is 39 degree. What is the angle here, incidence? R2, 54 degree. Then we can say R2 is greater than C, critical angle. Therefore, total internal reflection will happen. No emergent ray from which surface? We are talking about AC. Since R2 is bigger than the critical angle, no emergent ray from AC. Next one. Complete the path of the ray in the following diagram. So we are talking about 54-degree total internal reflection on this face, right? Then it has to be total internal reflection here. And then when it emerges from glass to air, it will deviate from the normal. That would be the normal here and the normal here. Ray diagrams must have the arrows. Right. This is how the ray diagram when 54 degrees the incident angle on the second surface. Clear? So that's a very simple experiment, right? There is nothing complicated in that. Just a couple of technical points regarding the practicality of the experiment. If you can understand that, the exam questions are very easy to answer. Clear? Let's practice this very well. We have some interesting experiments to do. We are going to take the spectrometer, calibrate the spectrometer and do experiments with spectrometer. Before we go to the spectrometer experiments, make sure you practice this very well, clear all your doubts and come to the next experiment.